Okay, let's go ahead and start. So, things that are happening. Uh, First of all, Mr. Merzinski's gotten back to me and he has said that his third exam will be on April 9th. And so, that exam is going to be going over basically chapter 2. So, solving equations. Everything that we've been going over this week in my class will be on Mr. Merzinski's exam on, again, Thursday, April 9th. Now, that also means that I also have an exam. And my exam, I'll have more information for you on how it's going to work and what we're going to do for it Monday. However, I can tell you that that exam is going to be given through Hawks. So, again, just make sure that you can get onto Hawks some way and get into that exam. And again, like I said, I'll have more information about that exam when we get to Monday. Let's go ahead and get into the lesson for today, though. So, yesterday we left off with the idea of sets. Sets being numbers that are kind of in a group. And we said that if we have something like x is greater than or equal to 4, that this represents a set. We can make set builder notation if we add a few things to this. But that stuff for our class doesn't really matter. The thing that we're worried about, the thing that we want to focus on is x is greater than or equal to 4. So if we want to visualize that set, we can use a graph on our number line. Zero being the middle. And let's say 4 is about right here. That's a weird looking 4. So because x is larger than or equal to 4, that means that we need to have a solid dot here to show that we can be equal to 4, and our set is going to extend from 4 into the things that are bigger than 4. And doesn't give us an upper boundary or anything. It just says that x must be bigger than 4, so it goes off into infinity. And we can also write this a different way in interval notation, so we don't have to look at this graph. We can instead look at the interval. The interval is a start point, which is 4. We read from left to right. And the end point, since we don't have an end point, really it's going to be infinity. Then we have to say whether we can be equal to these start points and end points. So can we be equal to 4? Yeah. And to show that, we will use a bracket. And can we be equal to infinity? No, we can never quite reach it. So we will use a parenthesis to show that. So again, this is what we call a set. And like I said, a set is just a group of numbers. Now, I also left us off with something called union, a new operator. It's an operator that's used specifically for sets. So if we have something like this set, x such that -2 is greater than x, and x is greater than 4, then our graph is going to be a little bit different. Instead of having a single line that we're going to be looking at here, we're going to be looking at two different lines. So we have this idea here that's -2 is greater than x, so we have to put -2 somewhere in here. We have x is greater than 4, so 4 again is about right there. We cannot be equal to -2, so we will use an open circle. And since -2 is larger than x, that means that x has to be smaller than -2. So our line is going to extend from -2 into -infinity. Similarly, x must be greater than 4, not equal to, so we're going to use open circle. And then x must be larger than 4, so it goes into positive infinity. Again, two lines. So when we write our interval for this one, we need to look at these lines separately. So first, this line right here, again, reading left to right, starts in -infinity, so that's our start point, and ends at -2. Okay, so can't be equal to infinity, can't be equal to -2. Then we have the second line. It starts at 4 and ends in positive infinity. Can't be equal to 4, can't be equal to infinity. But then we said that we need to show that this is really one idea. We have two separate lines, but it's one idea, this set builder idea here. So to show that it's all one thing, we use the operator union. It's the big U looking thing. Okay. So union is an operator. Like I said, it only works with sets, and it's like glue for sets. It takes two sets and puts them together. So here's another way of looking at that. Let's say that I have two sets, A and B. A is a set that has elements 1, 4, and 3. Oh, whoops, that should be in order, sorry. 1, 3, and 4. B is also a set. It has numbers -2, 1, and 5. So if we were to use union on this, again, it would glue both of these things together into one single set. So let's say we have A union B. Again, union is going to take these two things and glue them into one set. So we now have a new set. Where we have all of these numbers. Again, we're taking both these things, putting them into one set, making it one single idea. So we're going to have all of these numbers, and we list them in order from least to greatest. So -2, 1, 3, 4, and 5. And that's all of the numbers between the two sets. Now notice that both of them have the number 1. They share that in common. However, I did not list that twice because it doesn't need to be there twice. As long as it's represented, then it's there in the set. You don't need to list numbers multiple times in sets. And just to touch on another thing that we will probably see later on, there's another thing like union called intersection. So I'll show you what intersection does. Intersection is shown by an upside down union symbol. Intersection is not taking these and making them one set, but just showing what the sets have in common. So what do they have in common? They both have 1. And that's it. So union and intersection are kind of strange operators. They are very powerful, though. They do really interesting things when you get into a little higher level algebra. In fact, let me show you an example. So let's have a square here. I'll just sketch in some things. Okay. So imagine, if you will, that this is a map. Maybe a map of a county. And this county has gotten some funding to improve its infrastructure. An important part about that is improving bridges. Restoring the bridges, fixing them, whatever needs to happen on them. Well, an important thing to know then would be what distance is covered by bridges. How much bridge do you have in your county? Then you can know how much money to allocate to, fixing your bridges. Okay. So there's this thing called GIS. It's Geographic Information Systems. And what GIS does is it takes maps and breaks them up into information. One thing that it can do is break them up into sets. So one set that this map might have defined on it is water. Okay, so this squiggle here would be our water, our rivers running through this county. Another thing that it can do is roads. So these straight lines running through here would be the roads. And so what we can say is where we have roads that are overlapping water, that would be a bridge. Well, how do we define that? We use an intersection. Again, intersection finds the places that are common between two sets and lists those places. So if we do road intersection water, literally bridge, we can get how much distance is covered by bridges in this county. Which, that's a very, very, very basic example of using this, but I think it gets the point across. So, before we move on, are there any questions? Okay, I'm not seeing any questions, so we will move on. Alright, so we've seen what sets look like. Again, they're groups of numbers. Now, sets pop up in another place. Places like this. Okay, so this is an equation. We've been dealing with inequalities to find sets, but equations can give us sets as well. Very special cases, though. Places where we have squares, cubes, fourth powers, things like that. So let's see where this comes from. Okay, so here I have an equation. Y minus 8 squared is equal to 9. Remember that what we need to do in order to solve this is get the variable by itself. Well, right now that variable is tied up in these parentheses. And the thing that is locking these parentheses closed is this power squared. So if we want to get rid of these parentheses, what we need to do is get rid of the square. So we need to do the opposite of it. Just like if we have something multiplied by y, maybe it was like 2y, we need to divide by 2. We need to do the opposite of the square. So the opposite of a square, remember, is a square root. So we will take the square root of both sides. Okay, again, taking the square root of this side cancels out the square, leaving us with y minus 8. And then taking the square root of the other side, you might be tempted to say that's 3, which you're half right. The square root of 9 is 3. But like we've said before, now we need to start thinking about these square roots in a new way. Not only could the square root of 9 be 3, it can also be negative 3. So we have to say that this could be plus or minus 3. Remember that the reason we say this is because positive 3 times positive 3 is 9. Negative 3 times negative 3 is also 9. So we get this plus or minus thing here. Okay, well, one more step to get y by itself, and that is to get rid of that 8. Right now we're subtracting 8, so we're going to want to add 8 to both sides. So that cancels there. We are left with y on this side. And on this side, we have 8 plus or minus 3. So from this point, we need to actually break up that plus or minus into two different situations. One where we have y is equal to 8 plus 3. And another where we have y is equal to 8 minus 3. So 8 plus 3, that's going to be 11. And 8 minus 3, that's going to be 5. So y could be equal to 11, or it could be equal to 5. And there's how we get our set. We now have a group of numbers, not just one number, but a group of numbers. So y could be 11, or it could be 5. Okay. This is an idea called a quadratic equation. And quadratics will almost always have more than one answer. Typically, they'll have two answers. Sometimes they'll only have one. That's a very special case when that happens. But most of the time, you're going to see two answers because of this plus or minus thing. Okay. So let's try another one. So once again, we've got a square thing here, and that square is probably going to give us something that has more than one answer. Let's see how to tackle this, though. Well, just as it is, we could add 144 to both sides and then divide by 81 and take the square root of both sides. However, instead of just using normal solving skills here, let's try something different. Something we've actually used in the past but haven't used in this way. If we look at this side here, 81 x squared minus 144, this is a difference of squares. Remember that our difference of squares thing that we've talked about in the past always comes out to conjugate binomials. And again, we know that this is a difference of squares because everything here is a perfect square. 81 is a perfect square of 9, x squared is a perfect square of x, 144 is a perfect square of 12. And there's a difference between them represented by this minus sign. So we can actually factor this and say that this is 9x minus 12 and 9x plus 12. Again, it always comes out to be conjugate binomials. Okay? So what do we do from here? Well, there's an interesting idea in algebra called the zero product principle. And it says that if we multiply things together and the answer is 0, then one or both of those things has to be 0 itself. So let's look at this. We are multiplying this expression by this expression, and it's getting us 0. So one of these things, or both of them, have to be 0. And that's how we solve this. 9x minus 12 could be 0. 9x plus 12 could also be 0. So now we can go ahead and solve these. This is much easier to solve than what we had up here, the 81x squared minus 144. It's a lot easier to solve these broken down factored things than it is to try to solve this thing. Much smaller numbers, and we don't have squares anymore. Okay, so let's tackle this one. We need to add 12 to both sides. That gives us 9x equals 12. Then divide by 9 on both sides. Divide by 9 on both sides. Getting ahead of myself. That gives us x is equal to 12 over 9. Okay, well, of course, that can be reduced. So what can it be reduced to? Let's see. Both of those have 3 in common, so that would be 4 over 3. This one, same thing. Subtract 12, though, to get rid of it on that side. We get 9x is equal to negative 12. Divide by 9 on both sides, and we're going to get that x could be negative 4 over 3. So here's our plus or minus thing again. X could be positive 4 over 3 or negative 4 over 3, or we could just say plus or minus 4 over 3. So our factoring skills can come in handy when solving these things. Again, the original equation, we could add 144 to both sides to get rid of it here, then divide by 81 to bring it over here, and then take the square root. That's fine. If you want to do it that way, cool. Just know that it's not always going to work for all of our quadratic equations. Not all of them can be solved just by regular solving. Sometimes we are going to have to use factoring. And honestly, again, I think that this would be easier to solve with the factored form than it is with just these large numbers. So again, I'll pause and see if we have any questions. Okay, I don't see any questions, so let's move on. So like I said, sometimes we are going to have to factor. And that's absolutely true for this one here. So here we have 5x plus x. Why is that x? Messed that up when I was writing it. Oh, whatever, I'll just rewrite that. 5y plus 3y squared equals 28. Now I'll give you a tip here. Almost always, I'd say a good 99% of the time, we want to get these in standard form for a quadratic. And if you remember, we said that standard form for a quadratic is ax squared plus bx plus c. So we want our largest power out in front and then in order of descending power. So I'm going to rearrange this, and I'm actually going to have to take 28 over to this side to get this c term back over with these. So I'm going to need to subtract 28 from both sides, bring it back over here, and rearrange this so that it's in quadratic standard form. So our biggest power out in front, then the next smallest power, which is 5y, and then our c term. And it's all equal to 0. If you have your quadratic equation equal to 0, you're in a good place 99% of the time. It's usually a good idea to have these things, again, in standard form and equal to 0. Like I said, most of the time that's going to be a very good position to be in. And when in doubt, just do that. So, again, we need to solve this, but we have two different y terms, and they're y terms that we cannot combine. We cannot make this into a single y term. So, solving just our normal way is not going to work here because we can't make these a single y by itself. We're going to have to do something else, and that is factor this thing. So, remember our quadratic factoring starts with the AC method. Our A, this leading coefficient here, is 3. Our C, the constant term, is negative 28. So our AC would be 3 times negative 28. So that would give us 84. Negative 84. And we need factors of negative 84 now, something that will give us 5 when we combine them. Also remember that one of them has to be positive, one of them has to be negative because this AC is negative. So starting with 1 and 84. What else is going to work for us? Excuse me. So 4 and 21 works. Let's see. 2 and 42. Three. Whoops, lost my thing there. 3 and 28. Definitely need something bigger, though. $12 and 7 works. And yeah, that's going to be the one that we're looking for. So, remember that, again, we need a pair of factors, one of these pairs, that's going to give us 5, the middle number here, when we combine it. And one of them has to be positive, one of them has to be negative. So if we make this a negative 7 and this a positive 12, well, positive 12 minus 7, that's going to give us positive 5. So we can rewrite this now. 3y squared minus 7y plus 12y minus 28 equals 0. Again, all we're doing here is we're just replacing this middle term with the two that we found, equal it if we combine them. So we have 4 terms in our equation now, or our expression now, and we can either use factor by grouping or we can use the box method. I'm going to go ahead and use the box method just because I'm kind of pressed for space here. Oh my gosh, let's get a better box since I have the tools to make a perfect one. Okay. So, first term goes in the first box, 3y squared. Last term goes in the last box, negative 28. These two, doesn't really matter where I put them. I'm going to go ahead and take this negative 7y and put it here. And remember that its sign has to come along with it, but sits outside. Positive 12y, only one place for it to go. Whoops. Its sign again comes along with it, but sits outside. So we now factor our rows and columns. So common between these two numbers here is y. Okay. Then these two right here, 12 and 28, that looks like 4. This column here, we have 3 and y. They both have 3 and y. This column here, they both have 7. So, our factors, factored form, comes out to be 3y minus 7 times y plus 4. Okay. So now we have this in a form that can be solved, because remember, our zero product principle says that if we have two things that we're multiplying, or three things or four things or whatever, but if we have things that we're multiplying and they come out to be 0, then one or both of these things must be 0 itself. So we can say that 3y minus 7 could be equal to 0. And 4 plus y, I'm sorry, y plus 4 could be equal to 0. So solve this one here. We get that y is equal to 7, equal to 7 over 3. Here, y is equal to negative 4. And there's our two answers. Okay. So, again, I will pause for any questions. All right, I'm not seeing questions, so let's move on. I'm actually going to save this one for a moment and go down to this one. So, again, it helps if we have things in standard form. So I'm going to go ahead and take this 13, bring it back to this side, so we can have this in standard form equal to 0. So plus 13 to both sides. And now we're going to have x squared plus 20x plus 19 is equal to 0. Okay. So we could tackle this one as an AC problem. 1 times 19 is 19. Factors of 19 that get us 20 are 1 and 19. We could go from there. I actually want to show us a different way of doing this. There's yet another way of solving these things, and that is the complete the square method. Basically, what we're trying to do with these factors is break them up into things that we know multiply together to get the original thing. However, the complete the square method says that no matter what we have, we can put it into a form that we know factors a certain way. So we don't have to start guessing things like, okay, what factors do we need here to get to 20? We can just kind of force this thing into a form that we know factors. And factors a particular way. It gets rid of all the guessing and whatnot. So I'm actually going to show you that way, because the factor by grouping method can be faster if you get practice with it. Now, follow along with me, because some of the steps can be a little confusing, but again, once you get some practice with it, it makes a lot of sense. So what we want here is a perfect square trinomial, and a perfect square trinomial has a particular form to it. And I'll show you how to get that. First, look at your leading coefficient. Is it positive 1? Well, here, yes it is, so we're in luck. We can move on to the next step. I'll show you one where it isn't, though. So if it's positive 1, we don't need to worry about anything. We can move to the next step. The next step is to take the constant, in this case 19, and move it to this side. Remember, the constant is the thing that doesn't have any variables on it. So I'm going to move 19 to the other side. Now we have x squared plus 20x equals negative 19. Okay, next step. We need to actually force this thing to be a perfect square trinomial. And the way we do that is we take this term right here, 20, which looks like 26. Let me fix that. We need to take this number right here, 20, take half of it and then square that. So half of 20 is 10. 10 squared is 100. We will add that to both sides. This is a perfect square trinomial. You can tell that something is a perfect square trinomial if you take half of this number, square it, and you have this number here. And they factor a particular way. That's what's nice about this. Now we also need to figure out what negative 19 plus 100 is. So 100 minus 19, in other words, is 81. So now we have x squared plus 20x plus 100. That's a little weird looking. Equals 81. So the way that these perfect square trinomials factor is take this variable here, write it down, x. Take half of this number, write it down, 10. Take this sign and drop it down, plus. Make the whole thing squared, and it is now factored. This is the factored form of that. Again, you take this variable, drop it down, this sign, drop it down, take half of this, drop it down. Okay, now we can take this and solve it normally. It is factored now. We don't have to worry about that x squared term. It's factored. So this, like we said with the first example in this set, this set of parentheses is being locked by this square. We need to get rid of that square. So the opposite of squaring something is to take a square root. So we'll take the square root of both sides. And I'm going to bring this up here so we have more space. We now have x plus 10 is equal to, well, square root of 81 is not just 9, plus or minus 9. Okay, so really 1.5 more steps to go. We just need to take 10 to the other side. So now we have x is equal to negative 10 plus or minus 9. So let's go ahead and do our plus or minus thing. X is equal to, let's see, negative 10 plus 9 is negative 1. Negative 10 minus 9 is negative 19. So there's our answer. Any questions? All right, let's move on. Same thing. We want to use complete the square to solve this one. However, if you look at this one, the thing that's different is that our leading coefficient is not 1. So, like I said before, if our leading coefficient is 1, we're in a good place. We don't have to worry about much. Here, though, our leading coefficient is 5. So the thing you have to remember, if you want to complete the square, this needs to be a leading coefficient of 1. Well, what we do in order to make that happen is we take this leading coefficient and divide it off the entire thing. So everything, 5x squared, 5x, 30, and 0 is all going to get divided by 5. Whoa. Okay, so 5x squared divided by 5 is just x squared. Gives us our leading coefficient of 1. That's good. Negative 5x divided by 5 is negative 1x. Negative 30 divided by 5, that's going to be 2. I'm sorry, not 2. What am I saying? It's going to be negative 6. 0 divided by 5 is still 0. Okay. So now, again, we want to complete the square. So the first thing to do is to take this number, bring it to the other side so we just have the x's. So I'm going to add 6 to both sides. That cancels there. We now have x squared minus x. Oof. Is equal to 6. And now to make this a perfect square trinomial, I need to take half of this number and square it. So half of 1 is 1/2. 1/2 squared is 1/4. So we need to add 1/4 to both sides. Again, you can tell something is a perfect square trinomial if half of this number squared is this number. Okay. So I need to add 6 and 1/4, so 6 over 1, multiply that so we get a common denominator. That's going to be 24 plus 1. Okay, so 25 over 4. X squared minus x plus 1/4 equals 25 over 4. And again, I'm going to bring this up here so I have more space. All right. So remember that we factor this thing by taking this variable, this sign, and half of this number, so that's 1/2. And this whole thing is squared. Then this side is still just 25 over 4. Alright, we need to take the square root of both sides so that we can get these parentheses out of here. So we'll take the square root. That leaves us with x minus 1/2 equals plus or minus, square root of 25 is 5, square root of 4 is 2. Alright, so last thing we need to do is to add 1/2 to both sides. Let's add 1/2 to both sides. So now x is equal to 1/2 plus or minus 5 over 2. So 1/2 plus 5/2 is 6/2. So x could be 6/2. Which really we know that 6/2 is 3. Or 1/2 minus 5/2. That would be -4/2, which is -2. And there's our two answers. X could be 3 or -2. Okay, so complete the square, again, with practice, can be a much easier way of solving these things. Much quicker. And it comes down to the fact that if we make a perfect square trinomial like this right here, where this middle term, half squared, equals this third term, it factors the same way every single time. We take that variable, write it there, take this sign, write it there, take half of this number, write it there, and then the whole thing is squared. Now, it's going to be important to be able to recognize this, because that example that I skipped actually has a perfect square trinomial in it. So, this example, -14x and 49. If we look at these two numbers, what is half of 14? 7. What is 7 squared? 49. This is already a perfect square trinomial. So we can go ahead and factor it the way we know it goes. Take this variable, write it down. Take this sign, write it down. Take half of this number, write it down. Whole thing is squared. Okay. So now we can go ahead and take the square root of both sides. Here it's just going to give us x minus 7 square root of -121. Ooh, square root of a negative. Well, remember, before we left on our break, we went over these imaginary or complex numbers. And we said they come from negative square roots of negative numbers. So the square root of -121 is plus or minus 11i. Okay, so now we need to add 7 to both sides. And we get x is equal to 7 plus or minus, come on, 11i. And that has to be our final answer right there. Ugh, that's terrible. That's awful. Let's just use a box. Still learning how to use this thing. Okay, so why is that our final answer? Well, remember that I is a different type of term. It is not a like term to 7. 7 would also have to have I on it for us to be able to combine that. So that's actually our final answer right there. Some people will actually separate this out into x equals 7 plus I and 7 minus I, but you can leave it like that. I won't really be a stickler for that. And in fact, I'd prefer, for myself at least, I don't know about Mr. Mrzinski, but I'd prefer for myself that you write at 7 plus or minus 11i. So again, these perfect square trinomial things are quite useful because they factor in a particular way. And if you can recognize them, just like with our difference of squares, if you can recognize them, it really helps you figure these things out. Because, okay, I know I have a perfect square trinomial. I know how to factor this thing. I can just keep on going. All right. So I think that will do it for today. Again, remember that we have an exam coming up not next week, but the week after. So we will continue with this idea of factoring and whatnot, and then get some extra practice. And other than that, just if you need help, of course, remember that my office phone redirects to my cell phone now, so you can call my office phone on the syllabus, and it'll get me on my cell phone. Also, there is the Smart Thinking tutoring system that is on Blackboard. I sent out a tutorial on how to use that in one of the emails. And stay safe out there. I will see you when I see you, hopefully. So have a good day, and just keep on keeping on.